This is the second episode of my more intuitive model of quantum mechanics. In this episode, I want to talk about Heisenberg's uncertainty principle. As in the first episode, I'm using two postulates to try to make quantum mechanics more intuitive. First is that quantum objects are instantly reformable wave packets, all part of one thing. The second postulate is that they might instantly reform when interacting, depending on how much is interacting, according to the Born rule, where probability of collapse to a region is proportional to the squared amplitude. In the first episode, I talked about these two postulates at length. If you haven't watched that episode, you might want to. Otherwise, let's move on. So, what I want to push in these later episodes is that varying the parameters of wave packets gives us interesting quantum phenomena. So, in this episode, we're going to be talking about varying the size of a wave packet versus its wavelength, and this will give us the uncertainty principle. In another episode, I want to talk about confining wave packets, which gives electrons around the atom. And what about allowing wave packets to interact and join? That'll give us entanglement phenomena. So let's focus in on varying the size of wave packets and what effect that has. Wave packets are important for this presentation, so I just want to go over them again. Wave packets are traveling collections of waves, and they're constructed mathematically by combining an infinite number of waves together. And if they're all of different wavelengths and frequencies, they'll cancel themselves out in some regions, but in one region they won't cancel themselves out, and that's where you get the wave packet. Here you can see the effect of adding successive waves together. And here's a one-dimensional drawing of a wave packet, and here's a two-dimensional drawing. Suppose you have a wave packet that is larger than its average wavelength. Just by looking at it, you can basically tell what the wavelength is. Now, to construct this packet, you had to take a bunch of waves that were basically all the same frequency and wavelength and add them all together. And so you have a sharp frequency distribution for the packet. However, since the packet is large, you have a poorly defined position. You don't know where it's going to collapse to along the wave packet if you make it instantly reform. On the other hand, if you have a packet that is more comparable to its wavelength, to construct this one, you had to take a bunch of different wavelengths and frequencies and add them together, and there's a much broader frequency distribution. So when you make it instantly reform, you don't know what frequency you're going to get. However, you do have a very good idea of where it's going to instantly reform because the packet is so small. So you have a well-defined position, but a poorly defined wavelength and frequency. Now, one of the fundamental facts about quantum mechanics is that energy actually relates to the frequency of the wave packet, and momentum relates to the wavelength and thus also the frequency. So, with this in mind, we can look at a small packet which has a broad range of frequencies, thus also has an actual broad range of possible momentum. So, before you detect it, you don't know what momentum or frequency you're going to get, but you can be sure of the position. And interestingly, if you take this to an extreme, an infinitely small packet would have all possible momentum. Okay, so if you have a large packet, you have a definite frequency and thus a definite momentum. So you can be quite sure of what momentum you're going to detect before you do. Make it instantly reform, but you don't know where it's instantly going to reform to. You can't know the position. And interestingly, if you take this to an extreme, an absolutely definite wavelength occupies all points in the universe. Now we can appreciate the uncertainty relationship, where you have the uncertainty in position times the uncertainty in the momentum is greater than h bar over 2, where h bar is based on Planck's constant, which is one of the fundamental constants of the universe. So as we all know, 1 divided by a large number gives you a small, and 1 divided by a small number gives you a big number. So we can rearrange the uncertainty relationship, and if we have a small uncertainty in the position, that gives us a large uncertainty in the momentum, and that corresponds to this situation where you have a broad distribution of momentum but a small wave packet. And of course, if you have a small uncertainty in the momentum in this rearrangement, and that will give a large uncertainty in the position, and that corresponds to this situation. Let's look at an uncertainty principle example where we collide a high energy X-ray photon with an electron, and the electron packet instantly shrinks and the X-ray is scattered off. So this is scattering of an X-ray. So from the scattering you can figure out where the electron was by where the photon came in and where it came out, basically triangulate. And that allows us to know the position. So now the position is certain, but what happens to our knowledge of the momentum? Well, we've just shrunk the wave packet, so now it's quite small, and now the momentum is uncertain because it's a small wave packet. So if you try to measure the momentum just after the collision, like a really short time interval, you don't know what you're going to get, but you do know what position you're going to get because you just scatter the photon off of it. So we know position, but we don't know momentum. Now, interestingly, if we wait some time and allow this system to evolve, the packet will actually enlarge because the momentum is uncertain and the wave packet is going in multiple velocities in multiple different directions. So because the momentum is uncertain, and over time the position will then become uncertain. As a final example of the uncertainty principle, let's look at a proton going through a velocity selector. Velocity selector consists of a magnetic field, in this case coming out of the page, and that deflects the proton into a circular path, and then you have a screen here with a small hole in it. Now, if the proton makes it through this small hole, you have a very good idea of what the momentum is, because only those protons with the exact right velocity will make it through. So from that, maybe you think, maybe we can figure out where the proton is going to be based on the time it entered. But you can't do that because it's a wave packet and it just went through a small hole. So it's going to spread out. And if it spreads out, you can't figure out where the position is going to be. It could be here, here, or here. You just don't know. So the uncertainty principle is a fundamental law of nature, and there's no getting around it. And I'd just like to acknowledge where I got the images and animations that I didn't make up myself.